All right, so now that we know roughly what we want to use graphs for and what kinds of graphs we want to define, now it's time to define graphs rigorously. So how do we do that? Well, remember the objects we're trying to define look like this. So we have something with nodes and between them edges. So how do we define this in a mathematically rigorous way that will give us exactly what we want to have? Well, this is a way. So we define a simple graph to consist of two things: a set of vertices and a set of edges. Now, the set of vertices is required to be finite and non-empty, just a set that's finite and non-empty. And the edges are pairs of vertices. I will discuss a bit more in a moment what we mean by distinct unordered pairs of distinct vertices, but let's look at an example. So suppose we want to have this kind of graph. Say we have nodes x, y, z. So then if this is our graph G, then this corresponds to the vertex set just being the set of three elements x, y, and z. And the edges, well, we have one edge between x and y and another edge between y and z. If you want to be pedantic, you should really put brackets and commas between the elements inside the edges, but this takes time, so we will not do that. So this graph, the picture that I drawn, will correspond to this set of vertices and this set of edges. So remember, vertices and edges are just abstract names, but of course this is what we think of them as, these dots and lines in a picture. Now, what do these fancy words mean? So the fact that our edges should be distinct pairs means that we do not allow multiple edges. So if we have a vertex x and a vertex y, this would mean that the pair xy occurs twice, and we don't want to have that. The fact that the pairs are unordered means that we don't have any direction. So if we have x and y, this edge, we can call it xy, we can call it yx. It doesn't matter, it's the same thing. So there is no first vertex and second vertex, there's no arrow of direction. And the third point, which is a subtle point, is this distinct vertices. So the vertices x and y, in order for there to be an edge between them, they must be different. So we cannot have a vertex that has an edge to itself. So this thing, edge from x to x, is not permitted. And with these three conditions, we get what we call a simple graph. Now, sometimes we will want to allow some of these things, and this leads us to the more general definition of a graph. So a graph consists of, again, a finite set of elements called vertices and a finite family of unordered pairs of vertices called edges. So please pause the video here and go back and forth between the definition of graph and simple graph and see what the difference is. So here, as an example of a graph, now we're allowing something like this. So a graph G that has, say, a multiple edge between x and y, and then for good measure, a loop in y. So here the vertices are x and y, and for the edges, we have the edge x, y, counted twice, and the edge y y. So what have we done compared to the definition of a simple graph? We now allow multiple edges. So we allow repetition, and that's why we call this a family of edges rather than a set. Because remember, when you have a set, an element either is in the set or not. It cannot be counted multiple times. That's not how sets work. So if you want to allow repetition, you need to call it a multi-set or a family. Depending on the book, different words will be used. But the point is we allow multiple edges. And also this word distinct vertices is gone. Now we allow loops. However, we still require the pairs to be unordered, so we have no direction of our arrows. So this is how you define a general graph. Now, please be cautious. This is the definition that we'll use in the course and the definition that is used in the book. But if you pick up a different book, they might use words differently with respect to direction, loops, and multiple edges, so be careful. So, okay, so let us take a look at some small graphs with 1, 2, and 3 vertices. And let's, to simplify things, just look at simple graphs. So how does a simple graph with one vertex look like? Well, you have one vertex, and since you don't have a loop, you cannot have loops, there is no possible edge. So this is the only graph with one vertex. We can call the vertex X. Doesn't matter too much. Now, I would like to ask you to pause the video and think about which possible simple graphs we can have with two vertices. Ready? The answer is we have two possibilities, because between our two vertices, call them X and Y, either this is what we have or we allow an edge. We cannot allow loops, we cannot allow multiple edges, so these are all the possibilities. With three vertices, we get different versions. We can have just the three vertices, X, Y, and Z, with no edges. We can have versions with one edge. With one edge, we can have the edge between our X and Y vertex. We can have the edge between X and Z. We can have the edge between Y and Z. Then we have all the versions with two edges. So these are all the versions, all the three graphs with two edges. And of course, we can have all three edges. There we go. So these are all the simple graphs with 1, 2, and 3 vertices. Now let us take a closer look at some of the features of these simple graphs. In particular, let us say look at this graph. So this is one graph, but it looks like it consists of two pieces that sit next to each other. X, Y looks like one graph by itself, and Z looks like one graph by itself. And this brings us to the notion of connectedness. So when you have a graph, roughly speaking, it is connected if somehow all pieces sit together like that. If the graph looks like this, it's disconnected, because here you have X, Y, Z in one part, and then here maybe U and V sit differently. So this graph is the union of two components. What we mean by that is the following. So the union of two graphs is basically you take the two graphs and you draw them next to each other. So you have two graphs, G1 and G2. The union of the two graphs has vertex set union of the two vertex sets, and the edge family is the union of the two edge families. So, for example, in our previous example, we have our G1 here and our G2 here. I am being lazy and not labeling the vertices, but then the union of the two graphs is this graph sitting together. And what does it mean for a graph to be connected? It means that it doesn't look like this. More precisely, a graph is called connected if it cannot be written as a union of two different graphs. If it can, it's called disconnected. And so, since any graph is the union of connected graphs, because you can break it into the so-called connected components, really the philosophy is it's enough to understand connected graphs, since all graphs can be built up from connected graphs in this way. And so in many of the theorems and applications that you will see, we will only consider connected graphs because that is enough.